Okay, let's start our practice by looking at question 4.43, which simply asks us to draw the ring flip for the following compounds. Remember that a ring flip is not a flip like a pancake. It is a change in conformation. So we're actually talking about rotating bonds. So we have this molecule, or we have the hydroxyl here, we have a methyl, and we also have a chlorine. So there's the molecule, and we want to draw the ring flip. So when we draw the ring flip, you see how you have a point up and to the right here? Well, the point is going to be up and to the left in the ring flip. So up and to the left, there we go. And again, if you want to do these by using a template when you're practicing, that's totally fine. So I'll clean up my structure a little bit. All right, so if we number the atoms, if we call this 1, 2, 3, 4, 5, 6, you can try the same thing here. So what was pointing up here, right, when you do the ring flip, that's going to be this carbon here. So we'll call this 1, 2, 3, 4, 5, and 6, like that. So if the methyl group is pointing up and is axial, in the ring flip, it's still going to be pointing up, but it's not going to be axial, is it? It's going to be equatorial. So at carbon number 1, we have to draw a methyl group that's going up and equatorial. Notice how my methyl group is parallel, or as best I could, to these two bonds. That's the equatorial position, right? The axial position at carbon number 1 is going to be pointing down like this, and it's going to have a hydrogen on it, right? If you follow these two bonds, that carbon number 1, the axial position will be pointing straight down. All right, so let's move on to carbon number 2. We have a hydroxyl, which is up and equatorial. So that means here it's going to be up and axial. I have a question for you. On the second conformation on this one, will the hydroxyl be pointing straight up or straight down? And it's not a trick. Yeah, it's going to be pointing straight up. Exactly. All right. There we go. So going to be going straight up. So our hydroxyl is going to be going straight up like this. And then the chlorine is down and axial here. So in our conformation, or our other conformer, it's going to be pointing down. But if it's down and axial in one conformation, in the next one, it's going to be down and equatorial. So I'm going to draw a line down like this. Again, notice that this bond is parallel to these two bonds right here. Again, as best I could. So there is the ring flip, my friend. So we've got to do that for a couple more. So let's try 4.43b, which asks us the same thing. We're just starting with it's actually an isomer of this compound. So we'll start by drawing the best chair I can. Maybe I need a chair template in my iPad. Anyhow, so we have a chlorine going up here. We have a hydroxyl pointing up here. And then we have a methyl group pointing down like that. So we're going to draw the ring flip. Start by drawing something that looks like this. Draw the chair to get started. There you have it. So if we number the carbon, so if this is 1, 2, 3, we can just do that much. And this would be 1, 2, 3. So if the chlorine is going up and is axial here, it's still going to be up in the other conformer. However, it's going to be up and equatorial. So we have it up and equatorial. How did I know to draw the equatorial position like this? Remember, if you draw it straight out like that to try to fool someone, that's not correct. Okay? And I know that you would never do that, but it's not correct. Every once in a while, I have a student who kind of draws sort of a hybrid, and I'll say, that's not right. You got to show that the chlorine is actually going up, right? This bond is supposed to be parallel to these two lines right here. Now, on the second carbon, we've got two substituents, right? We've got the hydroxyl and the methyl group. The hydroxyl is going up. Since it's up and equatorial here, it's going to be up and axial here. So we'll draw a bond straight up to our hydroxyl. And then our methyl group is down and axial here. So it's going to be down and equatorial over here. And I'm going to draw a bond just like that. Remember, I tried to make this bond parallel as best I could to these two bonds right here. And there we go. Give me a thumbs up if you got something close to that. Maybe I should give you a little more time for the next one. So I'll draw C, and I'm going to give you a minute to try it yourself. Instead of just watching me do it, you want to give it the old college try, right? You never know where you stand, really. Nobody does until they try themselves. So let's start by drawing a chair. Okay, so there's a chair. And I have to use my pixel eraser to clean them up after I draw them. You know, one of the things that I see as an instructor, and the reason why we don't ask too many questions about drawing chairs when we're face-to-face in class is because I'll always get somebody drawing these, okay, a bow tie, and you cannot figure out what's going. They'll draw a bow tie, and then they draw bonds like this, you know, and bonds, you know, going like this and stuff. So you cannot tell. I mean, it's totally wrong. And I'm not saying that you would do that, but I'm just saying I've seen it before. And so that's why we don't harp on this for too long, because it is challenging. You know, it does take a lot of practice to master chair drawing. You can see that mine aren't even perfect. You don't draw them enough anymore. All right, so there we go. And we have a chlorine going up like this. So we draw the ring flip. And we'll do this. Here we go. There's our ring flip. We'll number the carbons. So 1, 2, 3, 4. 1, 2, 4, like that. If my hydroxyl is down, right, this is down and equatorial. So that means in my new conformation, in the ring flip, carbon 1, it's going to be pointing down, and it will be axial. If my methyl group is pointing up and is equatorial, that means that on carbon number 3, it should be pointing up, and it should be equatorial. So up and equatorial would look like this. Okay, right, I tried to draw it parallel to these two bonds right here. And then for my chlorine, it's pointing up. On carbon 4, it's up and axial. So this is, or sorry, up and equatorial, I meant. I'm thinking about the answer. So then on carbon number 4, it would be up and axial. Well, like that. Comme ça, as we say in French. What do you think? Give me a thumbs up if you're following me, or stop me if you have a question. Does everybody just follow me on the concept? Of course, it's going to take some practice. It takes everybody practice. You get the weekend to work on it. You know, drawing a chair is challenging enough. Challenging for everybody. Don't ever think like, oh, I'm the only person that can't draw a chair. It's difficult. You know, it's not an easy thing. As you've heard me say, what, probably 100 times during this class. If it was easy, right, if organic chemistry was easy, and it's not, everybody on the street would be able to do it. But just the fact that, you know, very few people to study organic chemistry because it's a difficult subject. All right, but it doesn't mean it's not a fun subject. It's still a very fun and exciting subject. Let's try one that's, let's get out of the cyclohexanes. Well, not entirely, are we? Let's try number 4.47. This is the type of question that, so concept, the parallel lines. Okay, yeah. So when we look at a chair, if you look at a chair, so we'll just take a chair like this. Okay, like that. Okay, a chair is made up of 3 sets of parallel lines. Right, these 2 lines are parallel. These 2 lines are parallel, and these 2 lines are parallel. So I went over drawing the axial positions, right? You have 3 axial positions that are pointing up like this. You have 3 axial positions that are pointing down like that. So we discussed the axial positions in detail, but when it comes to drawing the equatorial positions, they're a little more complicated, I think. But the equatorial positions are always going to be parallel to a set of the lines in here. So if I look at this carbon right here, if I circle this carbon in green, you look at both bonds that are connected to it, and then you go 1 bond away from that. So the 2 bonds in green are going to be parallel to the equatorial bond here. Okay, so the same thing here. If you move over to this carbon, you have this one and this one, then you go 1 more bond away from it. What have you got? You've got these 2 yellow bonds. So this equatorial position is going to be parallel to the 2 yellow lines. If you move over here, you've got this one and this one, then the 2 blue lines are parallel. Okay, same thing here at this carbon, right? You have this bond and this bond, but the 2 green lines are parallel. So you always go, again, 1 bond away on each side. So this one is going to be parallel to the green one, right? If you do it here, it's going to be parallel to the two yellow lines, right? You go one away, and then you draw one that's parallel like this. And then for this one, you go one bond away on each side. What's parallel is the blue ones. So you draw a line that's parallel to the blue. So again, you see how this bond and this bond are parallel to the blue lines. You see how this bond and this bond are parallel to the yellow lines. And you see how this one and this one are parallel to the green lines. And that's how we determine the the equatorial positions. So there we go. All right. Remember that you have the solutions to all these in the solutions manual. So if you just click on the question number on 4.43, it will open up the solutions. Does that answer your question about the equatorial positions? Does that help? Okay. All right. Yeah, however you do it is fine. I mean, everybody's got their own strategies. You just have to find a strategy that works for you for drawing in all the equatorial positions. And you know, you can use the book strategy or the ones that I showed you, you know, where you draw in all the axial positions like this, and you draw the axial positions like this. Okay, there you go. Let's move on to question 4.47. It's a little bit different, 4.47. So this question asks you to draw a bond line structure. So draw a bond line structure, okay? And they give you a Newman projection, which is kind of cool. They give you this Newman projection. So you've got a methyl group up here. You've got, you just fill it all in here. So we've got a methyl group here. We've got a proton here. We've got a methyl group here. We've got a methyl group here. We've got an ethyl group here, CH2, CH3, and then we have an ethyl group over here. This is a real classic, like MCAT type problem, where they just give you something that looks really simple, you know, just drawing a bond line structure. I mean, everybody in the class can draw a bond line structure, but it's not that, you know, simple when you're given a Newman projection, but you've got to be able to do it. But remember that this point right here where these three lines intersect, that represents a carbon. And this whole thing, this whole circle in green right here, that also represents a carbon. Okay, so if we count up the total number of carbons in the molecule, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9 carbons in this molecule total. So when you draw your bond line structure, if it doesn't have 9 carbons, you did something wrong. So what I like to do with these problems is I'll start by drawing the blue carbon. Okay, this is the carbon in blue, and then it's connected. Maybe I'll just write it in blue like this, and it's connected to the carbon in green, right? The one in the back. Well, what's on the carbon in blue? It's got 2 methyl groups and a proton. So it's got 2 methyl groups and a hydrogen. What's on the carbon in green? It's got a methyl group. It's got 2 ethyl groups. So let's draw that. It's got a methyl group. Oops, let me just draw a bond line structure. It's got a methyl group and it's got 2 ethyl groups like that. So there you go. That's the skeleton of the molecule. So then if you want to draw a bond line structure, I mean, you can tidy that up. I mean, you've got a total of what? How many carbons in the longest chain? You've got 1, 2, 3, 4, 5. So you could just go, you could just make it a little prettier. 1, 2, 3, 4, 5. And we have a methyl group over here. We have a methyl group here. Oops. I draw that correctly. 1, 2, 3. So, oh, I put my methyl group in the wrong place. There we go, like that. And then we also have an ethyl group here, like this. So there you go. There's the bond line structure of that compound. Nothing more than that. All right. But it's not that simple. You know, I don't think it's an easy thing to do. I don't like to use the word easy in a chemistry class, but I don't think it's, you know, the simplest thing in the world, okay, to draw a bond line structure from a Newman projection. So there you go. Boom. And that is the bond line structure. Let's try another one. Let's try B. So this is 4.47b. Let me get my pen back. There we go. So if we draw the carbon in back, got the carbon in front, it's got a methyl group attached to it. Okay. Then we have a hydrogen coming down here. We got another hydrogen here. We got this bond, and we've got this bond, and then they are connected like this. And then I have a methyl group coming down like this. All right, I'm going to give you a second to try this one before I show you the answer. I'm going to give you a minute. Take a drink of water. So there's a ring in this compound, isn't there? Can anybody tell me how many carbons are in the ring? All right, there's 5 carbons in the ring. Exactly. So look, if you're unsure about that, let's start by drawing the carbon in blue, okay? And then it's going to be attached by a bond to the carbon in green. So where's my green carbon? Here, right? And then in between them, you have 1, 2, 3 CH3s connecting them. So 1, 2, 3 methylenes connecting them like that. On the blue carbon, you also have a methyl group, right? You've got a methyl group and you've got a proton. And then on the green carbon, you've also got a methyl group and a proton like that, okay? So if we were to draw a bond line structure for that, all we have is a cyclopentane with 2 methyl groups, but we're not done. This isn't done. Can anybody tell me what I'm missing here? There's something very important, that this structure isn't complete. The connectivity is correct, technically, but there's something that I'm missing right here. Could anybody tell me what it is? It has to do with the relationship of this methyl group and this methyl group. So if you're unsure, I can help you out with it. The methyl group on carbon, the methyl group on the blue carbon is pointing up, isn't it? Right, this one's pointing up, right? And then this one is pointing down. So they are trans to each other. So the one on the blue carbon is going to be pointing up like this, and the one on the green carbon is going to be pointing down, and that would be the correct bond line structure. You have to show that those are trans to each other. All right, if you look at this carbon, the methyl group is pointing up, the hydrogen is pointing down, so we could even fill in the hydrogen, right? And I mean, you don't have to, it's a bond line structure. All right, if you look at the carbon in green, the methyl group is pointing down and its hydrogen is pointing up. So you could write the hydrogen like that if you want. Anyhow, we'll leave those out because they don't have to be there. All right, let's move on. And I have some other questions that I thought are really good ones. Let's try questions. So this is question 4.50. Question 4.50, I made a note to myself. This is a question I asked on a quiz one year. So if you want to know type of things I think are good questions. So question 4.50 gives you the structure of menthol. So let's draw just the 2D structure here. So we've got a methyl group that's pointing up here, hydroxyl here, and then we have an isopropyl there. So it says menthol, isolated from various mint oils used in menthol cigarettes, right? Is used in the treatment of minor throat irritation. Draw both chair conformations of menthol and tell me which one is a lower conformation in energy. So let's draw both chairs. So let's start by drawing one chair, and then let's do it like this. We got one chair like this, and then we have the other chair like this. Okay, and then we're going to flip the ring and we're going to determine which one of these is the most stable conformation. All right. So I'm going to give you a second to try drawing one of the conformations. I'll give you a minute here to try that. All right. So if we number these carbons as 1, 2, 3, 4, call this one 1, 2, 3, 4, and then we'll call this one 1, 2, 3, 4, like that. We'll just leave 5 and 6 out because there's no substituents on them. So the methyl group here, this is pointing up, this one is pointing up, and this isopropyl group is pointing down. So in the first molecule, or the first conformation, this one here, will the methyl group be axial or equatorial? It is not a trick question. Will the methyl group here be axial or equatorial?
Axial.
Absolutely, right? It's axial. So we have the methyl group pointing up like this. So if we go over to the third carbon here, we have the hydroxyl pointing up. Remember, if this is up and axial, this would be up and equatorial, this will be up and axial. So it means the hydroxyl is going to be up in axial, like that. And then we have the isopropyl group, which is going to be going down on carbon 4. The down position on carbon 4 is also axial. So everything in this conformation is axial. I mean, holy smokes, have you got some 1,3 diaxial interactions here or what? I'm kind of giving the answer away. But if we move over to the other conformation, which I don't really have enough room for here, do I? Let me erase these and I'll just move it over a smidge here. There we go. So on carbon number 1, the methyl group is up, but now it's going to be equatorial. On carbon number 3, the hydroxyl is pointing up, but it is equatorial. And the isopropyl group is going to be down, and it is equatorial. So maybe I'll take the whole thing and I'll move it down here. Okay, and then I'll take this one and I'll move it over here. So if I call this one A and I call this one B, who could tell me which one is going to be more stable? Which conformation would be lower in energy?
A.
It's not going to be A. It's going to be B. Because, right, in A, we have a bunch of 1,3 diaxial interactions. We have them here between the hydrogen and this hydroxyl. We have them between the hydroxyl and the methyl group here, and this hydrogen and the methyl. We have them with the isopropyl, right? And these protons here, we have big 1,3 diaxial interactions here. Whereas in B, we have no 1,3 diaxial interactions. So no 1,3 diaxial interactions, since everything is equatorial. So the answer is whenever the substituents can be equatorial, it's going to be favored. Okay, now if you have a battle, if some are equatorial and some are axial, you would want the bigger substituents to be equatorial. But in this case, everything here is axial and everything over here is equatorial. So B is going to be the more stable of the two conformations. So more stable, right? Because again, we have no 1,3 diaxial interactions in the second conformation. All right, let's try question 4.52, which looks at the same type of thing, where we're looking at conformations. So this is 4.52. It says for each of the following pairs, determine which is more stable. So the question is just which conformation is more stable, but they don't give you chair conformations. They give you structures in 2D like this, and you have to determine which one is more stable. Now, if you're really quick, And if you really understand the concept, you can answer these questions without drawing a chair. But since I'm the instructor and since we're learning this, I think the best idea would be to draw the chair. All right. So again, this is question 4.52. All right. So we'll call the first one A. We'll call the second one B, just for fun, like that. All right. Before we even start, does anybody have an idea which one of these would be more stable? Would it be A or B? I'll show you how to solve it without drawing the chair. So I'll get a bunch of people saying A. All right. Nobody's saying B. Yeah. Okay. Well, let's take a look at A, and then we'll take a look at B and see if we can figure it out. So let's imagine, since we have two substituents that are on the same side and they're alternating, right? These are 1 and 3 substituted. If this was up and equatorial, let's say, that means that this would also be up and equatorial, right? So if this one would be up and axial, this position, this hydrogen would be up and equatorial, which means that this is actually down and axial. So what does that mean? In this molecule, this most stable conformation, we'd have 2 equatorial and 1 axial. Whereas in B, let's imagine that this is down and equatorial. If this is down and equatorial, then the down position here would be axial. The down position here is equatorial. So that means that this is also down and equatorial, and this is also down and equatorial. So in this one, you have a conformation where everything is equatorial. And so the answer is B is going to be more stable because you have a conformation where everything is equatorial, and there is no conformation that you could adopt for A where everything is going to be equatorial. Even if you flip the ring, if you were to flip this, this would become axial, this would become axial, and this would be equatorial. All right, give me a thumbs up if you just follow me on that. If you're like, yeah, I understand it just by looking at the structures without drawing the chair. All right, so we could try. So hold on, Warren, the question is, it's asking you which conformation is going to be more stable, right? Because even if you flip the ring here, you still end up with a conformation where you have 2 axial and 1 equatorial. So this, what we've got labeled here, where you have 2 equatorial and 1 axial, is still the more stable of the 2 possible conformations. Yes, you could have a conformation here where everything is axial, but it's asking you which one of these would give you something that's more stable. And the answer is only B could have a conformation where everything is equatorial. Okay, so it's not saying, oh, well, what about the highest energy conformation? They're just asking you for which conformation is more stable, because remember that the equilibrium is never going to be 50-50 if they're different conformations, right? The equilibrium is going to lie to the side of the one that is more stable. It's a good question that you asked. It's a very good question. It shows that you understand what the hell is going on. But if we draw A, and I'll do it a little quicker than I did the first bunch of times. All right, if this is going up and axial, that means that the next one is going up and axial, and the next one is so first one is, no, sorry, that's not how I wanted to do it. I wanted to draw it so everything was equatorial. So let me redraw my ring. So I'll do it like this. So this is up and equatorial, this is up and equatorial, and then this one would be down and axial like this. Sometimes we like to disconnect the bond, maybe like that, to show that it's going behind the page. Right, whereas in this one, the most stable conformation, right, Warren, the most stable of the conformations has this one going down, right? This one is going down, and this one is going down, and everything is equatorial. And so this one is going to be the more stable of the 2. All right. I just looked at the solutions manual, which I normally don't do, but they didn't even draw anything. They didn't draw anything. All they have is a text answer. So I think that you're supposed to be able to solve these problems just by looking at the 2D structure. Let's try another one to see if we can really, get confident on it. Let's try B. So this is 4.52B. 4.52B. So we got, again, 2 cyclohexanes. So we have a methyl group going down, we have one pointing up, and we have it going down. And then we have this guy here, which has the same connectivity, but it's a stereoisomer, right? The arrangement of the atoms in space is different. So here we go. If I call this one A and I call this one B, could anybody tell me which one of these would be more stable? Just by analyzing these. And Warren, maybe they should have written the question a little different. Maybe they could have said, you know, which one can adopt the more stable conformation, right? Because they are isomers. Yeah, Jessica, Warren, you're both correct, right? It's A, isn't it? Right, why is it A? So if you're not 100% sure, let me show you why. Okay, if this, we'll start with this methyl group. If this is up and equatorial, what does that mean? When you go here down, the down is going to be equatorial because up, down, up, down, up, down would alternate and they're always going to be equatorial. So that means that this would be down and equatorial, and this would also be down and equatorial. Whereas here, same thing, if this is down, if this was down and equatorial, let's say it was, okay, then this would be down, down and axial, and then this one would be up and axial, wouldn't it? So then you've got two groups that are axial. And if you're like, well, couldn't I flip it so that this one, okay, if you flip the ring, then this would be equatorial, this would be equatorial, but this would still be axial. Okay, and in the first one, we have a conformation where everything, every stinking thing is equatorial. Give me a thumbs up if you follow me on that. Or if you don't, stop me and take a harder look at it.
I was trying to ask this question with the last slide. No, I'm not following. I'm not following in terms of the I guess the stripes versus the solid line.
So
how determining which one is axial and which one's equatorial.
So you can choose, right? So when you have a dash or a wedge, right? If you have a cyclohexane, let's say, okay, all these mean are up and down, okay? This means up and this means down. Do you follow me on that? So a solid line or a solid wedge means that it's pointing up and that the dash means it's pointing down, correct?
Yes, I'm following that. I'm just not understanding the alternating of it. If on the chair model, if it goes up, if it's 1, 3, and 5 are going to all be axial on the chair model, and then that means 2, 4, and 6 should be equatorial, correct?
Yes, if everything was pointing up, yeah.
Okay.
Or if everything was pointing down, right? Let's say we had 6 wedges, right? If you draw all of these pointing up like this, so everything, all 6 of these methyl groups are pointing up, but they alternate. If this one's axial, the next one would be equatorial. This one would be axial. This one would be equatorial. This one would be axial. This one would be equatorial. If you were to flip the ring, so if you were to change the conformation so that this one is now equatorial, right? Then it would make this one axial. It would make this one equatorial. It would make this one axial. It would make this one equatorial, and it would make this one axial. So it's about the ring flip. They're always pointing up, right? Because they're all wedges. But when you flip the ring, it alternates between up and axial and up and equatorial. Does that help?
No. Okay. So looking at number B and the 4.52 that we currently have here. Part A, if we're just looking at that one and we designate the solid as an equatorial, why is the next dashed line that's going, well, no, okay, that one actually makes sense there because that would then be, no, it doesn't. On part A, if the solid line going up is equatorial, why is not the next dashed line that's going down axial? If they're 1, 3, 5 are supposed to all be the same.
No, but these aren't 1, 3, 5. This is arranged 1, 2, 3.
I understand if you were completing the whole ring, right? If the solid line is supposed to be equatorial, meaning it's going up, I would assume how I'm seeing it is then, and we're assuming that first solid line is 1, the next dashed line is 2.
Yeah, you can number
And the
them.
next solid line, or the next line would be 3, which would then be solid, right? And then the one across from the solid would then be a dashed line, and so forth and so forth. I'm just completing the ring as if they were all like a methyl group.
So we're talking about this ring right here, correct? The one I have in the yellow circle?
Correct.
Okay, so let's redraw it. So if we draw it like this, okay, make it a little bigger. So if we have a methyl group pointing up, okay, you could label that as axial or equatorial, but the point is it's pointing up, right? And then you have a methyl group here that's pointing down. You have another methyl group here that's pointing down. So if it's up and axial, okay, you could label it up or in axial or up and equatorial. It doesn't matter, okay? So if you said it was up and axial, right, the next axial position is going to be pointing down because axial alternates up, down, up, down, up, down. So if this was up and axial, right, the next position would be down and axial, okay? This position over here is down and it would be axial. So if you were to draw,
it's the up versus the down, not just whatever angle. I was assuming that next angle, the one that's listed as down, is also designated as an equatorial, but it is not because it's listed as an up and a down. Okay, I got it.
Right, so if you draw the chair of what I'm just representing here, let's say, okay, so let's say we call this carbon number 1, we call this 2, and we call this 3. So we have 1, 2, and 3. So on carbon number 1, the methyl group is pointing down. So if it's pointing down, it's going to be down in axial. Let me get the black. So it's going to be pointing down in axial like this. On carbon number 2, the methyl group is pointing up, so it's axial. And on carbon number 3, it's pointing down, so it's also going to be axial, like this. All right, if we were to do a ring flip, let's say, so let me just move this over here. So if we were to look at the other conformation of the ring, which is the most stable of the conformations, okay, so if we were to draw it like this, and if we were to call this, carbon number 1 here, 1, 2, and 3, like this, okay? So if 1 is down, right, it's going to be like this. It's going to be down in equatorial, the methyl group, right? On the next one, the methyl group will be up, but it won't be axial. It will be up in equatorial. And on the third one, it will be down, but it won't be axial again. It's going to be equatorial, right? So these are in equilibrium with each other, but the equilibrium is going to lie to this side, right? So that's when we analyze these two rings. So the one that I'm putting in the yellow circle and this one, they're the same compound. They're just different conformations, right? Okay. Like if I have this one in the yellow circle, it's this. And the way that I've labeled this one, it's this conformation, right? So we're comparing conformations is what we're doing. Does that help?
I figured it out. It's the down, down, up, up. I got it. Thank you.
Okay, good. All right. There we go. Let's try another one. Let's try C. So C is in the same vein. So staying with the same question. So this is 4.52 C. And here we've got 2 methyl groups pointing up like this. And then we've got this one here where we've got a methyl group going down. And we've got another one pointing up like that. All right. So if I was to call this one A and this one B. Could anybody tell me which one of these would be more stable? Yeah, it's A. So Kyla says, and the reason it lies on this side is because there's 1, 3 axial. Yeah, so I think you're going back to this question here. But yeah, the equilibrium will lie hard to this side, right? Because here you have a holy host of 1, 3 diaxial interactions, right? Between the methyl groups down here and then the hydrogen with this methyl group here. But there's no 1, 3 diaxial interactions. Anyhow, getting back to this question, 4.52. Yeah, it's going to be A. Right? It's going to be A. Why? Because even if we don't draw the chair, if we just imagine this as being up and equatorial, right, then this position, the hydrogen that's pointing up like this, and maybe I should use the black pen. So this hydrogen that's pointing up, it's up and what? It's up and equatorial. So that means that this position is also going to be up and equatorial. What does that tell you? It tells you that the two substituents that you have are equatorial. So if I move over to B, and let's say we choose this methyl group that was unchanged, if we say that this is up and equatorial, that tells you that the hydrogen here, right, is still up. It's up, but it's axial. And that tells you that the hydrogen that's pointing up here, right, this hydrogen is up and equatorial. So what does that tell you about the methyl group? The methyl group is down and it is axial. So even if I was to flip this ring, I'm always going to have something that's axial, right? Because one methyl group is axial, one methyl group is equatorial. So even if I change the conformation, I still end up with one methyl axial and one methyl equatorial. Whereas in A, I have both of my substituents that can occupy the equatorial position. And right, the equatorial positions are going to be favored because they don't experience 1, 3 diaxial interactions. All right, let's move on from there and try question 4.53. So this is question 4.53, where we're asked to draw a Newman projection. So they give us this guy. So we've got a chlorine over here. We've got a bromine here. We've got a chlorine over here. And we've got a bromine going back like this. And what we're doing is we're taking our eyeball, there's my eye, and we're looking down this carbon-carbon bond, and we're going to draw what we see. So you can always start your Newman projection by drawing the back carbon and the front carbon like that. You can always start like that by drawing a donut with a very small hole. And then from there, you can kind of figure out what's going on. So I'll give you a second to try and draw that one. All right, so I have something that's going straight down. There we go. So if I circle this position in red, okay, could anybody tell me what would be at this position in red that I have the red circle on? Yeah, it's going to be a methyl group, right? Because the person who's viewing it is looking at this carbon, right? If I put a blue C here for this carbon, that's the blue C. So what's pointing straight down is this methyl group right here. So in that position, I have a methyl group right here. Okay, so in these two carbons, if I circle this one in red and I circle this one in green, one of them has a bromine and one of them is going to have a chlorine. Could anybody tell me which one is going to have the bromine? Would it be the red circle or where the green circle is? Yeah, it's going to be the one with the red circle, right? So this is going to be where our bromine is. Why? Because if the viewer is looking down this way through the molecule, anything that's going into the page, so this bromine and this bromine are going into the page, anything that's on the going into the page is going to be on the left-hand side, right? It's going to be on the left-hand side of the Newman projection. Anything that's coming out towards us is going to be on the right-hand side, will be on this side. Okay, so we get that sorted out. So that means that we're going to have a chlorine over here. And in the back, I'm going to have this methyl group pointing straight up. I'm going to have a bromine on the left-hand side, and I'm going to have a chlorine on the right-hand side, like that. So make sure that you spend some time drawing some Newman projections so that you're able to, nail those. So anything about a Newman projection. And with that in mind, I wanted to go back and try a couple of nomenclature problems. So now we're kind of going back towards the beginning of the chapter. Let me see here. There were some ones I wanted to look at. Let's try question number 4.36. 4.36F, I think, is a good one. It's pretty challenging. So this is question 4.36F. So just bear with me as I try to draw the whole thing here. There we go. I got a nice purple group here. Nothing group there. There we go. Like that. Okay, so we want to try to name this molecule. Maybe I could fix that a little bit. There we go. That's a little prettier. Anyhow, take your time, but I want, if somebody could just type in the chat what the longest carbon chain is in the molecule. If anybody finds the longest carbon chain, let me know. All right, where am I? Yeah, absolutely. My students are saying 10 carbons, right? You can see the longest carbon chain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in it. Right? So this is some kind of decane, and we have to figure out what that is. So am I going to start numbering from the end that I have circled in green or the end that I have circled in red? Can anybody tell me which end you would start numbering from? Yeah, from the end that's labeled in red. That's exactly right. I'm just double checking to make sure I have the structure written out here correctly. Did I write it out correctly? 1, 2, 3. Oh, I made a mistake in my longest carbon chain. Nobody pointed it out though. Let me see here. I started looking at it and I'm like, that's not right. What I had highlighted in yellow is, I mean, that is 10 carbons. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that. Then I have 1, 2, 3 substituents. Well, look, if I do this instead, if I go from here, from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then I have 1, 2, 3, 4 substituents. So we want to find the longest carbon chain. That's right, Warren, that has the most substituents. So the one in green, or the line that I have in green, is correct because then I have more substituents. Right? If I had gone over here, then you have less substituents. So you want to find the longest carbon chain, with most substituents if you have a tie. And this one has 4 substituents. There you go. So now we've got what substituents? We've got a methyl group here, a methyl group here. We've got an ethyl group here, and we have an isopropyl group over there. So as my student said, you're going to start numbering from this end up here because then you have 1, 2. If you were to start numbering over here, you'd have 1, 2, 3, 4, 5. You wouldn't have a substituent until the 5th carbon. You want to give the first substituent the lowest possible number, which would be a 2 versus a 5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So again, it's still some kind of decane, so that was correct. But now we want to number and name the substituents. So we've got 2 methyl groups, so we have a 2,4-dimethyl. Then we have a 3-ethyl. And we have a 6-isopropyl. 6-isopropyl. Like that. When we alphabetize, we're going to alphabetize the substituents. We ignore all prefixes except isocyclo and neo. So we've got the letter M, the letter E, and the letter P. So E is going to come first. So if we put all this together, we have what? We've got 3-ethyl, 2,4-dimethyl, 6. Mr. Dion needs some more coffee. I just said we ignore all prefixes except isocyclo and neo. And then I went and ignored my iso. So I have I, so E, and then I, and then M, right? According to alphabetical order, right? When I go A to Z. There we go. So I have, what was it? 3-ethyl. We have 3-ethyl, and then we have a 6-isopropyl. 6-isopropyl. There we go. And then we have a 2,4-dimethyl decane. Dimethyl decane. There you go. 3-ethyl, 6-isopropyl, 2,4-dimethyl decane. And again, the importance of knowing how to name compounds using IUPAC nomenclature, it allows you to communicate with other scientists all across the world. All right, when you're discovering a new blockbusting drug, let's say, you want to be able to communicate that with your friends. All right. Let's try another one. Let's try, let me look at them, see which ones I think are challenging. Let's try A. Let's start there. So this is 4.36A. So 4.36A. So we have one. I added an extra carbon here, didn't I? There we go. Like that. And then here I've got this guy. Like that. There we go. So that's the correct molecule. So first thing we got to do is find the longest carbon chain in the molecule. You know where I think students would go wrong on this and why I think this makes a good problem is because, you know, if you, and I know none of you would do this, but if you were to just say, here's the longest carbon chain, if you're always looking for it to be horizontal and just kind of given to you, you'd say, well, look, I've got a sec-butyl group here. So that's 1, 2, 3, 4, 5, 6, 7. So this would be 3 sec-butyl heptane. But that would be incorrect, right? Because the longest carbon chain has what? How many carbons in it? Could anybody tell me?
7.
So it's got 8. The longest carbon chain has 8. If we go from here, 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain. All right, so it's some kind of octane. Like that, and we've got 2 substituents. We've got one here at carbon 3. We have another one at carbon 4. So this is some kind of 3-methyl. And then what's our other substituent? Can anybody tell me or identify the locant, the number, and what type of substituent the other one is? Yeah, absolutely. Absolutely. It's a 4-ethyl. So octane is the parent. And the substituents we're going to alphabetize. We have E and M. Well, E comes before M in the alphabet. So when we put all this together, we've got 4-ethyl, 3-methyl octane. 4-ethyl 3-methyl octane. All right, let's try a bicyclic compound. I think that would be fun. Yeah, there's two bicyclics in here. Let's try J. So 4.36 J. 4.36 J. You have a bicyclic system here. There we go. And we looked at an example similar to this one in the last class. If you remember the last class, we looked at an example where we had a 6-membered ring and a 4-membered ring tied together like that. All right, so this is some kind of bicyclo something, right? You've got bicyclo, and then you have the 3 numbers that represent the bridges. And then could anybody tell me how many carbons are in the bicyclo system? Is it a bicyclo, hexane or heptane? Or how many carbons total are there in the bicyclic system? Yeah, it's a bicyclodecane, right? Because we have a total of 10 carbons, right? If you follow the bicyclic system, it's all of this. There's 6 carbons here, 7, 8, 9, 10. So there you go. So it's some kind of bicyclodecane, right? So we'll erase all that. So we've got a bicyclodecane. We have the 2 bridgehead carbons here. Before we start numbering the bridges, right, we're going to have 3 numbers in here, 1, 2, 3. Could anybody tell me what the 3 numbers are for the bridges before we even get into, naming or numbering the substituents? Could anybody tell me what the numbers would be for the bridges? You go from the largest bridge to the smallest bridge. Yeah, Kayla. Yes. Okay. So Kayla, Bruna, you're both correct. It's 440, right? Because we have a bridge here that's got 4 carbons in it. We also have a bridge here that has 4 carbons in it, right? I've identified the 2 bridgehead carbons in yellow, and I have no carbons in here. So it's going to be, like my students said, they're correct. It's 440. So it's some kind of bicyclo 440 decane. I could click that more a little bit. All right. So what were the rules for numbering the substituents, right? We got a whole bunch. We got 1, 2, 3, 4 methyl groups. So 4 methyl groups, how are we going to number the rings? We always have to start at a bridgehead carbon. Let's say if I circle this one in blue and I circle this one in green, could anybody tell me which bridgehead carbon I would start on? Would it be the one with the green circle or the one with the blue circle on it? Yeah, it's the one with green, right? Because since both of these bridges have 4 carbons, I can start going either way, but I want to start on the green carbon, right? I want to start numbering down here so that I can give the substituent the lowest possible number. Now, if I go like this, if I go 1, 2, 3, like this, like that. If I number my ring like this, I skipped a carbon here, didn't I? It's like, that's not right. There's 10 carbons in the ring. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Then I have methyl groups at carbons 2, 3, 5, and 9. If I was to do it like this, so let me erase all this, which is going to be a lot of work, but let's do it here. If I was to start numbering from the top carbon, like this, if I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this, then I would have methyl groups at carbons 2, 4, 5, and 8. Now, I go for the first point of difference. These ones are the same. So this is my first point of difference, and 3 is lower than 4. And so the first way I had it done was correct, and this way is incorrect. So let me erase all these, and we'll go do it the correct way again. So I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I've got a 2,3,5,9 tetramethyl. There we go. So I've got 2, 3, 5, 9 tetramethyl bicyclo 4,4,0 decane, like that. And that is the correct name for this bicyclic compound. All right. Good. Let's try one more bicyclic compound. Let's try K. So this is 4.36K. So I'll draw this to the best of my ability. So we have a bicyclic system like this. That, and we've got a methyl group here, and we have another methyl group here. Maybe I can clean this up a bit. There we go. So we have a bicyclic system, and we have, let's start with the bicyclo. It seems to go faster that way. So we have bicyclo, something, something, something. Could anybody tell me how many total carbons are in the bicyclic system? How many total carbons would be in the bicyclic system? So there'd be a total of 8, right? In the bicyclic system, we have 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's 8 carbons in the bicyclic system. So this is bicyclooctane. Okay, then we have 3 bridges. We've got 2 carbons here, 2 carbons here, and 2 carbons here. So every bridge has 2 carbons. We have a bicyclic 2, 2, 2 octane. All right, and we have 2 substituents. So if I circle this bridgehead carbon in red, and if I circle this bridgehead carbon in blue, could anybody tell me which carbon I would start on for numbering my bicyclic system? Exactly. Thanks, Bruna. It doesn't matter. It doesn't matter at all. Somebody says either one, right? It doesn't matter because it's a symmetrical molecule, right? There's a plane of symmetry down the molecule. So I can start here and I can say 1, 2, 3, 4, 5, 6, 7, 8, like that. Works totally fine. So I've got a 1,4 dimethyl, right? Because I have a methyl group at carbon 1 and I have a methyl group at carbon 4. So this is, let's see here if we can put it all together. We've got 1,4 dimethyl, and then we take the rest, bicyclo 2,2,0 octane, and that is the name of the compound. Just like that. All right. Kind of running out of space there, but you get the idea. All right. So.